All right, today we're going to crack open the programmer's mind. But hey, don't worry, we're not here to write a bunch of code. Nope, we're here to solve puzzles. We're going to explore something called computational thinking, which is kind of like the secret framework for solving problems like a master detective. So, let's start our investigation, shall we?
I mean, have you ever just looked at some complex app or system and thought, how in the world does a human mind even begin to build that, right? How do programmers take this huge, messy problem and somehow turn it into something that's logical and actually works? It honestly feels like magic sometimes, but it's not.
Well, here's the secret. They think like detectives. Seriously, they look for clues, they spot patterns, and they followed this really logical process to crack the case. And that's exactly what we're going to do in this explainer. We're becoming logic detectives, and we're going to crack open a few mystery case files, pieces of code, to figure out exactly what they're trying to solve. Okay, so our first case file is all about this simple little variable called count. We've got a piece of code running, and this counter, it just keeps going up. Our job, figure out what in the world it's actually counting. The clues are all hidden inside the logic. So the code is working on a data set that looks something like this one. Now, to compare everyone with everyone else, it uses this really clever trick called a nested loop. Just think of it like a loop inside another loop. The outer loop will pick one student, let's say student A. Then the inner loop kicks in and cycles through everybody else, comparing them to student A. Once that's done, the outer loop just moves on to student B, and the whole thing repeats until every single possible pair has been checked off. Okay, now this is where the logic at the heart of the mystery really comes into play. For every single pair of students, the code is checking two things. First, is their gender different? That's condition 1. And second, is their town or city the same? That's condition 2. This is where the real detective work begins. And boom, here it is, the key clue that cracks the whole case, the OR operator. What this means is that the counter goes up if either of those conditions is true. It doesn't have to be both. So the code isn't just looking for, male and female students from the same city. It's counting any pair with different genders or any pair from the same town or even both. And that's the secret. Case closed. Awesome. One case down. But for our next mystery, we're going to need a brand new tool in our detective kit. It's time to talk about a super powerful data structure that's just essential for organizing clues, the dictionary. So what exactly is a dictionary? Okay, forget about code for a second. Just think of an old school address book. You look up a key, a person's name, to find their value, their phone number. A dictionary in programming, it's the exact same idea. It's just an incredibly efficient way to store and find information by linking a unique key to a specific value. Now, dictionaries have a few simple but really powerful rules. First, every key, like a name in our address book, has to be unique. You can't have two entries for Rahul, for example. The values, though, they can be duplicated, so two different people could totally have the same score. And it's super easy to update a value, like if you need to change a score later on. And this shows you exactly what I mean. Here, Rahul is the key, and his score, 92, is the value. If we want to know Rahul's score, we don't have to search through some long, messy list. We just ask the dictionary, hey, what's the value for the key Rahul? And it instantly gives us 92. It's fast, it's organized, it's just plain smart. All right, now that we've got dictionaries in our toolkit, let's tackle our second case. This one, it's a bit trickier. The data is kind of organized like a maze, and we're going to need our new tool to find our way through it. So the big twist in this case is that we're dealing with what's called a nested structure. It's not just a simple dictionary. It's a dictionary where the value for a key is, well, it's another dictionary. I know, it sounds a little complicated, but let's break it down. It's not so bad. Okay, so here's how this data maze is built. The main or outer dictionary uses a city as its key, but that key doesn't point to a simple number. Nope, it leads to a whole new inner dictionary. And inside that inner dictionary, the key is a gender, like male or female. And that key finally leads us to the value, a student's physics mark. So to find a mark, you have to go through the city first, then the gender. Now listen up, because this right here is the single most important clue in the entire case file. As the code is processing new student scores, it looks at the score that's already stored in our dictionary, and it only replaces that old score if the new one it's looking at is less than what's already there.
So, what does that tell you? It tells us the code's real mission. By only ever updating with a smaller value, it's constantly searching for the minimum, the lowest number it can find. So by the time the program is done running, this complex nested dictionary is going to hold the single lowest physics mark for both males and females in every single city in the dataset. And just like that, mystery solved.
Okay, so far we've seen how to follow logic in lists and how to organize data for a quick lookup. But what if the most important clue isn't the data itself, but the relationships between the data points? Yeah, our final case requires us to think not in lists or tables, but in networks. It's time to start thinking in graphs.
Yeah, up to now, we've used structures that focus on order or on keys. But what if the most important thing is how items are connected? Like a social network of friends or a map of roads between cities. That's where graphs come in. They are all about the points, or nodes, and the connections, or edges, between them. Now, to solve this graph puzzle, we just need to understand how the connections flow. We're looking at what's called a directed graph, which is just a fancy way of saying the connections are one-way streets, shown by the arrows. With that in mind, there are two key terms we need. The in degree of a point is simply how many arrows point to it, and the out degree is how many arrows point away from it. That's it. Okay, let's apply this to our puzzle. The code is zeroed in on this central point, node 4. First things first, let's find its in degree. All we have to do is count how many arrows are pointing into it. If we trace those connections, yep, there's only one incoming arrow, the one coming from node 2. So our in degree is 1. All right, next up is the out degree. Simple enough. How many arrows are pointing away from node 4? Let's look at the diagram again. And we can see just one arrow leaving, pointing over towards node 3. So the out degree is also 1. Easy peasy. And right here is the solution to our final puzzle. The code, which might look a little intimidating at first glance, is actually doing something incredibly simple. It calculates the in degree, then it calculates the out degree, and it just adds them together. So for node 4, that's 1 plus 1, giving us a final answer of 2. See? It's a pretty simple calculation once you know the language of graphs.
So we've cracked 3 different cases today, all by looking at code not as a language to write, but as a series of logical clues to figure out. And in doing so, we've actually built a really powerful problem-solving toolkit for ourselves.
So what's in our new Logic Detectives toolkit? Well, first we learned how to break down a problem step by step, tracing loops and conditions to see what a process is really doing. Second, we learned how to organize our clues efficiently with dictionaries so we can get to information in a snap. And finally, we learned how to visualize the connections between things using graphs. These 3 skills, they're really the core of computational thinking. And that brings our little investigation to a close. But I want to leave you with one final clue. This way of thinking, it isn't just for programmers. Breaking down problems, organizing information, mapping out connections, these are skills you can use absolutely anywhere. So the real mystery is this. What everyday puzzle are you going to solve with your new Detectives toolkit? Happy sleuthing!